Okay, so let's put it all together. So now we're going to talk about which transformation should we choose, a power model or an exponential model. So the problem below is going to show a strategy that we can use. So on July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet in our solar system, originally named UB 313. The potential planet is bigger than Pluto and has an average distance of about 9.5 billion miles from the sun. Could this new astronomical body, now called Eris, be a new planet? At the time of discovery, there were 9 known planets in our solar system. Here are the data on the distance from the sun in astronomical units and period of revolution of those planets. I think astronomical units is like Earth distance to the sun. So describe the relationship between the distance from the sun and the period of revolution. So there appears to be a strong positive but curved relationship between the distance from the sun in astronomical units and period of revolution in years. Oh, there it is. Okay, so based on the scatter plots below, explain why a power model would provide a more appropriate description of the relationship between period of revolution and distance from the sun than an exponential model. So if you look at the two graphs, you could tell that this is the power model because it's taken the logarithm, or it's taken the natural logarithm of both the distance and the period, both the explanatory and response variable, as opposed to the exponential model. It has to be exponential here because it's only taking, it's taken the natural logarithm of your response variable only, not your explanatory variable. So definitely your power model is definitely a better model for this relationship because it shows a clear linear. This is still curved over here, so this is not what we want. If we are trying to transform a curve to linear, then this has to be the better choice over here. All right, so the Minitab output from a linear regression analysis of the transform data is shown below. Give the equation of the least squares regression line. Be sure to define any variables you use. So because we chose a power model, we're going to take the natural log of both of your variables here. So we'll do hat natural log of the period equals, here comes your y-intercept, 0.000254 plus our slope 1.49986, and then it would be the log or ln of the distance. Okay, so that's all we needed. Okay. Now we're going to use that model to make a prediction. So again, we're going to have to make our prediction, but then we're going to have to kind of unlog it. So we have the ln or ln of the period equal to 0.000254 plus 1.49986 times natural log of the distance. So do we have here? 0.00254 plus 1.49986. And we're doing the natural log of 102.15. So that's going to turn out to be 6.939, but to predict the period, we have to undo the logarithm transformation. So we have period, is going to equal, because it's a natural log, we'll use base E. So to the 6939. Well, actually, it's about 1,032 years, which means we'll never actually know if our prediction's true. So a residual plot for the linear regression in part B is shown. Do you expect the prediction in part C to be high, too low, or just right? So Aries value for the natural distance, the 102.15 would have been, so I'm talking about this, ln or ln 12.15 would be 4.626, which would fall at the far right of the residual plot, because it goes up to 4, where all the residuals are positive. So because the residual is equal to your actual y minus your predicted y, it seems likely to be positive. So we would expect our prediction to be low. All right, so then in class I'm going to show you how to do all of this on the calculator, but it's a really long process. So you have the PowerPoint. We'll take a look at that together in class, and then we'll follow up that with this check your understanding. So that's it for this video. See you guys Tuesday.